confusing. Okay, so we'll try to do whatever we can. Hello, is my recording started? Okay, so I've already asked you to take the algae data set and you make a copy and we call it your algae Excel so that the original data set we kind of leave it intact. Okay, so let's look at your algae data set at this moment. Column A is just a numeric, that means an index number, don't have bother about it. B, C, D, season, size, and speed. Speed, I have no idea what is it. Okay. But B, C, D, they are categorical variables. What we want to see is looking at the algae growth, which is on column M. Can algae growth be predicted or be estimated by the media concentration, salt concentration in the media? Okay, so that's our focus. So let's look at this concept called correlation first. Correlation are talking about whether it's two variables are either trending up or trending down in the same way. Okay, so what you have for correlation, what correlation do you know? No. What are the measures you know? There are at least two that's listed in your or mentioned in your lecture notes. Huh? No, BMI. That means what measure? What are the two measures? At least. Correct. So you have Pearson's correlation. What is the second one? Spearman. Okay. So these two are person's name. Pearson's correlation is small letter r. In some places, it's also written as capital R. It's fine as well. Spearman is, okay, so let me just write it down. Pearson's correlation is small r or capital R, it doesn't matter. Rather than, okay, or capital R, doesn't matter. Spearman is R with a subscript S. Same thing, it's written in two different ways. What? R is actually just a symbol in this case. Okay. Now, so in your lecture notes, it's also given you what is the formula for Pearson's correlation. Do you still remember? Okay. So Pearson's correlation, the numerator is the data point of X minus of the mean of X, and the data point of Y minus of the mean of Y. Okay. The denominator is the same, but it is having a square. So if you look at just the numerics, let's say for example, it's in meters. So numerator is meters times meter, so it's meter square. Denominator is meter times meter times meter times meter, so it's meter to the power of 4. Right? So that's why you have square root, because it's to the power of 4. So let's get it back. Now, Spearman correlation, we don't really have to know the formula, but there's actually a formula as well. Okay. Which half of the time I have to go and find out for myself. So Spearman correlation is actually this formula. Okay. Is looking at D is the differences in rank. Yeah, they actually write. There's another symbol called rho, P as well. Yeah. This is not P, this is not rho. Correct. So there are a lot of symbols for the same thing. That's what makes it confusing. Okay. So it doesn't matter. Anyway, when do you use Pearson's correlation? When do you use Spearman correlation? Pearson's is when the data is normally distributed. That means the X is normally distributed, the Y is normally distributed. Okay. We call that a parametric measurement. Spearman is when one of the data is not normally distributed. out of these two, only Pearson's correlation you can calculate using Excel. Spearman correlation, there is no function to do it. But I'll kind of teach you how to do it as well. Okay. In R, you can do all this correlation by yourself. Okay. So in R, the correlation is actually inside your tutorial lab notes already. So I will not go through because by the time we go through your lab notes, it's actually far too much. So with that alone, let's say I want to correlate. I want to find the correlation, or if there's a correlation between these two values, which is the phosphate and the organic phosphate. Okay. But if you look at the data set, the very first thing when you get a data set, you have to scan through the data set. Are there values that are not filled up? Things like NA or dash. So that's a problem. If you have data like this, it means that data is not clean. You have to clean up the data yourself. That's called data cleansing. So how do you do data cleansing? There's actually multiple methods. The easiest way is to just remove them. Yes, manually. Okay. So think about it. Now there are 201 rows. So there are 201 rows. When you remove any row with NA, so it doesn't matter whether there's only one column, one cell with NA, or the whole thing is NA. Once there's one NA, you just remove it. But you document it down how you remove it as well. Okay. So let's remove it one at a time. What is the easiest way to remove it? You highlight the whole table and you do a sort. So you sort column by column. Okay, our most important is actually the numerical but let's say we sort column by column. Let's go to season. You go from, let's say, Z to A. Then are there any NA? So autumn. If there's NA, you should be somewhere in between spring and autumn, right? Okay, so it doesn't have. So you go to the next one. Because it's Z to A. And it's inverse order. You sort from Z to A. So where is N? Between which season? Okay, so size, same thing. So it should be between small and medium. So size is okay. Next is you go to speed. Okay. Speed is also okay. Then you go to the next column, which I can't remember what chemical it is. Okay, then you sort from largest to smallest. Numerical column, you sort from largest to smallest. Okay. The NA should appear on the top. Okay. Then you, let's say, for example, here there's only one. Kind of click it, right click, delete it. So you remove that whole column, whole row. Okay, so you continue doing it. Basically, you sort one at a time and find where all the NA values. So here, there's a lot. Yes, so you have to kind of remove them. Remove the entire row. Okay, after you are done, just do a Control F and look for NA. Make sure that you can't find any NA drop. You can. Then you do column by column, row by row. Then you do row by row. You can, up to you what do you want to do. The end result is you go from 201 rows to 185 rows. So which means that there's actually 184 readings. Let me show you it's all there. Okay. 105. Okay, so once you have done with this, we want to use it for R as well. So you take from column B to column M, copy, go to a new worksheet, go to a new spreadsheet, paste it in, and you save it inside the same directory. And you call it LG capital R. So later we use it for R. So we clear our data set already. Yeah, go and save it in R. Save it in as LG R. What? Create new workbook, paste the whole thing over. Okay, so now what you have done is you have a clean data set already, and make sure you are still in LG Excel. Don't go to the wrong sheet. Because you go for LG Excel, sort out everything, then save in LGR. Okay. So now you have 3 different versions of the same thing. Okay, so let's say we want to find the correlation between organic phosphate and phosphate. Do you think that there's a correlation? Should have, right? So how do you do a correlation in Excel? The easiest way is to use a formula. The formula is correlate, C-O-R-R-E-L. It's not the whole word, C-O-R-R-E-L. Then you need two data arrays, array 1 and array 2. It doesn't matter which one comes first. Okay, so I put organic phosphate first, then phosphate. Close it, and you have the correlation of 0.9. Okay, what? If you don't put in order, that's fine. Do the what? But how are they going? What formula do you compare? Compare what? Organic and the non-organic. Pearson's correlation. So this is Pearson's correlation. Okay, so this is Pearson's correlation. All right. Now, very often we want to do a overall correlation with everything. That means, for example, I want to look at manganese oxide. Is it correlated with chloride? Is manganese oxide correlate with nitrate? Is manganese oxide correlate with ammonia, and so on? Okay, that will be pretty troublesome if you want to use a formula method. So far, so good. So how do we do that? What you can do is use your data analysis toolkit. Okay, and look for this thing called correlation. Okay, correlation. Okay, and what you do for input range is select all the range that you want. So from column E to column M.
Okay, my data is actually in columns. I have the label in the first row. Press my mouse, what you want. Yeah, data analysis. Correlation. Okay. So I can put my result in a new worksheet. So I go to a new worksheet and I call it correlation. So the new worksheet will come out as correlation. Okay, then try to click OK, see whether there's any error. Okay. So this is the what we call as a correlation matrix. You do all the correlation for you for those that have numerical values. So you can find out the correlation for everything. See? It's only the lower triangular matrix because it's actually inverted. Just flip the whole thing over. Okay, so that is correlation. Pearson, when we talk about correlation itself, we're talking about Pearson's correlation itself. Now, Spearman correlation is not, there's no function in Excel that does Spearman correlation, but it's actually possible to estimate Spearman correlation in Excel. So how do we do that? Okay, the magic is this. Spearman correlation is actually the rank correlation. Okay. So what is this formula? N, you know, N is a sample size. The only thing that you don't know is D. The only thing you don't know is D. D is, yeah, D is difference, the difference of rank of A minus the rank of B. You can actually do that. That means you have to generate the ranks first. So let's say we want to do a correlation of, let's say, chloride and nitrate. So you copy these two columns, go to your correlation, put it in. We don't bother about the correlation matrix now. Okay. So try to put it in the same column L and M. Okay, otherwise you may have a little bit of problem trying to follow. And in column N, you type as rank of chloride. Column O, you type the rank of nitrate. So what you actually want to do is the whole chloride column, you sort it and rank in order. Then you do the same for nitrate and see what is the difference in the ranks. Make sense, right? So the easiest way, this, you don't mess it up, this easy to mess up. Highlight all four of them. Every time you highlight all the four columns, okay? Then you sort based on chloride first, so the first one. Okay, sort, the order is from smallest to largest. Okay, so you actually rank all the numbers. Anyone do in your secondary school do drills before, marching drills and all this? Okay, doesn't matter. Okay, so what you do is you type in yourself. So this is rank number 1, this is rank number 2, this is rank number 3, and so on. Again, you can double click. You can either drag it down or on this crosshair cursor, double click, it will fill out the whole column for you. Or you want to type 1, 2, 3, 4 all the way to 184, you also can. Okay. All done up to this part already? Okay, then you sort out the calcium column. You want to sort the nitrate column. Highlight everything. If you just highlight nitrate column and sort, then only the nitrate column gets sorted, which means all the data is wrong already. Okay, so highlight everything. sort the nitrate column, and you do the ranks again. So from 1, 2, and so on. Okay. Now, if you want to do the difference method, which is based on the formula itself, you can do it. Difference is just the difference in rank, one rank minus the other rank. Doesn't matter, because eventually in the formula you will square it. So it doesn't matter which one minus which one. Okay. But we are not going to use this method because it's a bit tedious. You can do the same thing if you really want to. Okay. You want to do halfway? Okay, fine. Then you do the yourself lah. Then here you can do square of difference. Then here you just produce a whole formula for yourself, square it. Okay. Then what you do is the sum of d square, which is equals to sum d square. Okay, then looks at the formula again. So okay, then you take 6 times this, divide by count of d square. Hold on. Let me see. 184, correct? 100 d square. How do you square d? Yeah. So I'm just producing the whole formula out. So it's actually n square minus 1, n square plus 1. See, yeah? N square minus 1, n minus n square. And so this is actually my Spearman correlation. Okay, and this is based on the actual calculation. So this formula is based on actual calculation. It's a bit tedious. I just take the S2, which is d squared times 6, divide by the denominator. So I use count to count the number of data points. If you want to make it extremely clear, then yeah, S2 is the sum of these two, d squared. It's a bit tedious, but it's doable. The formula is not very confusing. Okay, we get to that. If you don't get to that, it's also fine, because this is not absolutely necessary. What? What? Oh, I know what you do. Why? Huh?
Because the D square is not even there. Look at, calculate the D square first. D square. Huh? What is it nonsense? Yeah, just sum of the whole column. This is the sum. D square is the sum of D square is actually the sum of this column.
Possible? Who knows? Did your D square get correct or not? Okay, but is your Spearman correlation close enough? Okay, your Spearman correlation is close. Those that get a slightly different D square, your Spearman correlation is same to which decimal point? So decimal point. Actually, that's good enough already. Okay. All right, then what? Yes, what? Huh? Because your D square is nothing. Sum of this. Okay. All right. So based on this, right? Let's look at if we do our Pearson's correlation. Okay, stop talking. Pearson's correlation. Pearson's correlation is the correlation of the original data values, correct? This is actually Pearson's correlation. Yeah, it's just correlation. Correlation. Okay, if you have wrong answer, click on your column L, check do you have the correct number here. More data points or less data points. That means your data points, number of data points is wrong already. Check the count and check the sum. Here. 2, 5, 4, 6. Okay. So what we want is, instead of going through this whole equation, let's do our estimate of your Spearman. The estimate of a Spearman is simply use Pearson's correlation on the ranks. Not on the data points, on the ranks. On the ranks. If you do a Pearson's correlation on the ranks, you get almost a similar answer. It's pretty close already. Okay, basically the difference is like 0.05 or so. Okay, the reason is Spearman correlation actually borders about all the type ranks and all this stuff, so you don't have a border. Okay, so that is basically how you do kind of easy way to do Spearman correlation in Excel. Okay, next one, what we are trying to do is other stuff. Okay, let's take your algae all the way to E to algae, and put into a new sheet. Copy, never cut. Okay. So what we are trying to do is, can we predict algae growth through the composition? That means what I'm trying to do is this. Can I predict my algae growth as a function of maybe my phosphate concentration? So I will actually be doing this. PO4 plus C. Okay, this is what you learn in your general secondary school maths. Right, so this y equals mx plus c. Okay, this is the same. Y equals to mx plus c. Just that in statistics, we don't like to use m and c. Okay, because it can be quite confusing. So we use another term. Essentially, m is the coefficient of c, correct? Coefficient of x. Okay, c is actually the intercept. So we call all coefficients in this case y, or this will be algae. The coefficient the intercept is always denoted as beta 0 or b0. Then all the coefficients is beta 1, beta 2, and so on. So this is your linear correlation. This is called a simple linear regression. The purpose of regression is to get this deterministic equation. That means you can calculate for every possibility. Okay. And to see whether is this equation working well, we look at the Pearson's correlation value. If it's not good, we can actually add more variables to it. For example, stay step 1. Step 2, I can actually do algae equals your beta 1 of phosphate plus maybe beta 2 of nitrate or ammonium plus beta 0, and so on and so forth. Can be quite indefinite as I go along. What we call this as multiple linear regression. And we look at differences in models by also looking at the R value. So at the end of the day, what we are trying to figure out is what are the coefficient values to find out these numbers. Okay. So let's do that and see what happens. So for example, I want to do for algae and phosphate. Okay. And out of phosphate, I would say that maybe organic phosphate is more important. Okay. So I go to regression. Then I have the y value and x value. The y value or the dependent variable is my algae. Okay, so highlight the algae column. My independent variable will be the organic phosphate. Okay, this regression is a bit tricky, so just highlight the one with numbers. That means you don't highlight the entire column. Okay. That means you don't highlight the entire column, you only highlight up to the end of the number. That means I only highlight 185 rows. Okay, and because I have the labels, my first row is the label. I click on labels. The output range, I put it in, let's say, K1. All right. So once you are done, click OK yourself. You should get 3 tables. Correct. Later I'll talk to explain that. So you click OK, you get 3 tables. Okay. Now the first table you have is the regression statistics. You have the multiple R, the R square, and the adjusted R square. Usually we just take the multiple R.
R squared is just multiple R times multiple R. That's all. And multiple R is just R. Okay. All right. Then you realize that it gives you a Anova table. What do you think this Anova table is doing? It's doing Anova, but Anova, what is the hypothesis now? What do you think is the hypothesis here? The null hypothesis is this? No? Correct. The Anova table, in this case, is actually the null is actually testing the null hypothesis that R equals to 0. That means there's no correlation. Null hypothesis is testing that there's no correlation. That's why this, when you do your one-way ANOVA, this is supposed to be treatment, right? The treatment is regression, which means the treatment is this guy. The alternate is there is a correlation. R is not equal to 0. All right. But remember, what we are trying to figure out is this. What the coefficient. Okay. So that is the third table. If you highlight here, format the cells for you first. Now, so this is actually the one important table. Okay. What we are trying to fit is this model. Algae equals to beta 1 B1 times the concentration of your organic phosphate plus the y-intercept, correct? This is what we are trying to do. So what is the number of B1 and what's the number of B0? It is actually listed here, the coefficients. So you just rewrite these two into B1 and B0. So these coefficients, this part, you just rewrite it out. So you have algae. Okay, but you change the B1 to the coefficients for organic phosphate, which is minus 0.08655. And beta 0 is 22.09121. So that is the equation. We are done correlation already. We're running out of time as well. Okay. Up to here, any problem? Understand what's going on? Okay. Then, if you go further down, you have p statistic and p value again. What are they testing? What do you think they're testing? Correct. They are testing, put here. In this case, the null hypothesis, they're testing the null hypothesis that intercept, the coefficient for the intercept, the coefficient of intercept means B0 equals to 0. And here, the null hypothesis is that B1 equals to 0 or beta 1 equals to 0. So based on the p-value, it's unlikely that the coefficients are equal to 0. P-value. And you can also think that the coefficient is actually the mean value of the coefficient, the average of the coefficient. So if there's an average of coefficient, using your t statistic, you can find the 95% confidence interval, which is given here. The next one. So the actual range of intercept may be between 18.5 to 25.7. Huh? This one? Because this, another part is you can actually set for yourself. Just now we never set, we set the alpha equals to 0.05. You can change it. That's why the two things the same. So which means that the beta 1 can be between minus 0.057 to minus 0.11. Because it doesn't cover 0, therefore it is significantly different from 0. So that is how you read this table. All right. Huh? Go and watch my video. You explain it. All right. Okay. So this is the easy part. We move on to the next step. Because remember, we have only one metabolite. We have one chemical only. We have done this. How about the second part, which is this guy? The multiple regression part. Okay, we don't ignore it. Let's do it. So let's hide this whole thing. Okay. Okay, I will hide it. So let's just put it away. So what I want to do is, can I actually predict my algae growth using all the metabolites? Everything. So I have beta 1, beta 2, beta 3, beta 4, beta 5, beta 6, beta 7, beta 8, and beta 0. Okay, in Excel you can do it. Okay, you go to your data analysis tab, similar, go to regression, and the Y value, range remains the same. The thing that you change is the X range. X, you go from column 1 to column H, then you drag the whole thing down. So basically, column A to column H. Column A to column H. So from cell A1 to cell H15. Yeah, of course. Okay, then the output range. Output range we put in on, let's say, V1. Okay, just now Ken was saying that why there's duplicate of 95% confidence interval, right? Because you never change this one. So it's 95 and 95. This one don't bother about it. It's more complicated. Residuals, you are looking at the error range. Yeah. What? Yeah, of course, that's why we know over there. See, it's the same number, right? You see, go all the way to H. Okay. So when you click OK, this is where the first two tables is similar. Oh, you cannot hold. Then the third table is the one that's very messy. This is all the coefficients for the respective metabolite. Yes, these are all the beta values. And what it does is, it tests every single beta value is equal to 0 for you. That means it's y intercept equals 0. Is this equal to 0? Is this equal to everyone? So some of them may be equal to 0. If it's You cannot reject null hypothesis. The 95% confidence interval will be across the zero values.
How do you use the p-value? Intercept is
Is y-intercept possibly equal to zero? That's the p-value. That's a 5% chance, right? To reject null hypothesis. Then you do one at a time. This is one hypothesis. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9 plus original regression hypothesis with 10 hypothesis to test. Huh? There's no easier method.
So I come by this trade and you a new rule, let's say like
Okay. So these are all the coefficients. That means you can write out your whole regression. Huh? Intercept is B0, correct?
Okay.
Alright. Yes. That means it may be 0. This value may be possibly 0.
If we reject it, then it may be.
Oh my God.
If we reject, it should not be 0. If you accept, because the null hypothesis equals 0.
So the p-value is less than 0.05.
Then you reject null hypothesis. Null hypothesis is the coefficient is equal to 0. Don't bother, just look at it one at a time. Okay. Okay, so what is the limit of Excel? That means how many? See, there's 1, 2, 3, 4, 5, 2, 4, 6, 8, right? The limit of Excel is 16. We got the 16.
Yeah.
Yes, what? I want to. What happened? You start with 2 and here start with 1. More than 0.05. So what? This is more than 0.05. Reject null hypothesis, correct?
It's also
What?
more than
Like equals to 0. Okay. All right. So this is Excel as much as you can do with your multiple regression. All right. Okay. So does it still appear strange to you that why on earth it does something like this quite weirdly? One part of the regression analysis uses Anova, the other part of regression analysis uses t-test. Is it? You find it weird?
weird.
Okay. So why do you have Anova here? Why do you do an Anova test here and you do a t-test here? Why don't you do a Anova here and Anova here? Possible, right? Or a t-test here and t-test here, because degrees of freedom is 1, that means there's only 2, right? Yeah, so why not t-test here and t-test here, or Anova here and Anova here that you do? Now you have Anova here and t-test here. There's nothing to do with number of factors. Hey, your attention span is very low. Why do you have Anova here and t-test on the second part and not Anova on the first part, Anova on the second part, or t-test on the first part and t-test on the second part? No, it's actually not.
Okay. Later, I'll show you what happened. But keep that in mind first. So from here, now we are still Excel, we will jump into R. Okay. So in R, make sure that in your folder, there's this LG capital R already. Just now you asked you to save, right? Okay. So now you go to R. Original one. The original one you cannot use because you have removed, there's too many of the NA already. You have to clean it up. That's why I asked you to save it. Okay. Then similarly, you go and set the working directory to wherever you have your data file. Yes, session. Your R is what? Then how am I going to help you? Go to where your data file is located. You can, it's troublesome. Up to you. Make sure that you go to a working directory, you automatically write the command for you.
What? There's more.
Go to session, set working directory. Click a new session, use it. Go session, click a new session, set working directory, go to choose directory. And go find where the folder is. Well, it's not working like that. What? How do I know where your file is? No, you cannot open file here. It's opening the wrong file. Go to session, set working directory, choose directory, and go and navigate where you are. Anything you got the file. Then open up. Go back. It will be nothing. Open. Then you pop up here. Okay. So now your LJ capital R, you import the data set. You import the data set. Why? Okay. So you import the data set already, it should give you here. The LJ R is 184 observations of 12 variables. This is a valid Excel file. This is the Excel file. If the Excel file is open, then you cannot. 13 variables. Yeah, that's fine because your first column is added in. Some of you have 13 variables because you forget to remove the index column. That's okay. Yeah, that's where you have it. That's the problem. Okay, who else have problems? We'll help each other first. Okay, so those who are ready, we can do our regression. Okay. So regression, we start with a model, M equals to, you can put model up to you. Linear regression is, the function is LM, linear regression. Enter. Just a variable name. Linear model. Okay. Then we want to say that it's LG. LG is a dependent variable. The independent variable is PO4, phosphate. Okay. Make sure it is case sensitive. R is case sensitive. So your P and O, make sure it's capital. No, where the data is, data equals to your LG, capital R. Because that's a data file. Because this is capital R. Yeah, if you're nothing, then it's an name. All right. Then, yeah. Okay, you not give you anything? What is the error? Error in model frame. How do I know? You have error, what? Not me. Okay. This is the problem. You just screw up yourself because the algae and this algae is the same. So it doesn't know which algae to use. So you better change a new name. That is why I call algae out.
Okay, so I think ready. Then
saving as a CSV file. No. Funny that here you put algae growth. What's you going to change algae growth yourself? Then you change again. Peter is this guy. Yeah. What? How is gay growth? Use what? Use LM, not 1M.
Oh.
Oh, exactly. Okay, I got it, teacher. It's 1 and M.
It's LM, linear model. Since when I say 1M?
Oh yes, I got you. Bro, you're like
It's not, it's nothing happening. Okay, so once you have that, M is actually the model. So to produce the model, to get the results, just do a summary of M. And that is your model. The estimate is actually the coefficient.
Oh.
Then it provides the R square and the P value as well. So this is also the equivalent to the same part as your Anova table. This is the second, this is the third table.
Put on top.
On top, yeah, it just tells you what you provide. Okay. So remember, let's say in Excel, if we want to say, if we go back to Excel problem, right? If I want to do something like this, is algae equals to magnesium oxide plus nitrate plus organic phosphate. I can't do that. Excel will not allow me to do that. There's no function to do that. I have to put all these consecutives together as the X value. But in R, I can do it. I can just pick and choose whichever I want. Yes. So I can just go back. So phosphate, I can just add, let's say, magnesium oxide, and so on. Plus, for example, nitrate. Yes, it's case sensitive. Is that okay? Okay. Yeah, sensitive what? Just say the big O and the small n doesn't look as though there's much difference. Okay, so that is your multiple regression. Limits? No limit. R has no limit. What? R has no limit to the number of dependent variables. The number of independent variables. Okay, I've done 2,000 plus before. 2,000 plus. Yeah. Yeah. It's actually one of the things that was done last year or the year before.
So why would you need 2,000?
Oh, because I was trying to do this. I was trying to estimate, let's say, the growth rate of the cell is equals to looking at the gene amount. So from gene 1 all the way to gene 2000 or even more. So the multiple one.
What's the other side of
Gene 2000, beta then plus beta 0.
What the work after beta 2000?
Beta gene, no? So I got go from gene 1 to gene 2000 or even more. Then after that, I select which gene is important. Okay. Yeah, you can.
Wait, you have to check each and every one.
Actually, there are tricks to do around it, but it's already out of the syllabus, don't bother. Okay, So now, what? Okay, if you look at this, what is the look at my equation here, my command here. What is the difference between what you have done now and what you have done 2 weeks ago in Anova? Almost the same. There's only one thing that's different. Instead of using linear model, you use Anova. So you can actually do the same thing for Anova. It will give you. You just change the whole thing here, and you do your Anova. It technically does Anova for you. Okay. Just that this Anova doesn't make sense at all. But you can do it.
But no point.
No point, no point. Now, then remember Anova, what we have done is because why is this degrees of freedom 1? Because there's 2 and there's actually multiples. So Anova, remember the second, let's say algae growth, is it dependent on, for example, season? Right? For example, 2 weeks ago we did is cholesterol, the average cholesterol dependent on the body frame. So it's algae growth, the average algae growth dependent on season. Makes sense, right? What happened? Okay, if we go back to do Anova here, I will be doing something like this. Is algae growth depending on season, correct? So the average algae for each season should be the same. And I do a summary. I know 4 seasons because my degrees of freedom for season is 3. So that's 4. What do you think will happen if I change, instead of doing Anova, I do regression on this?
What do you think will happen?
What do you think will happen? Do you think it can produce something? Let's look at this, look at this number. Let's say if I were to bring this bit down, okay, I will just change this into regression. So I'm doing regression based on season. It will produce the individual seasons for me. Because if it is spring, then it's spring. If it's not summer, not winter, then it is autumn. Yeah. And what you realize is, if you go down, this is a little bit tricky. Look at our regression first. Our regression, our Anova, the F statistic is 0.405. The p-value is 0.7. Okay. The more important is the S statistic. We go down and see when we do the regression version, the S statistic is identical. Okay. So do you think there's a relationship between Anova and regression?
Yes.
Yes. Yes. The relationship is Anova is regression.
What is regression?
Regression is not Anova, Anova is regression. So Anova is a subset of regression. Yeah. Okay. If you want to see the proof of Anova equals regression, you can watch my video on YouTube. Huh? What?
Regression can do everything. In fact, regression can do Anova, regression can do t-test for you as well, because Anova is a part of t-test. Okay. Now, I don't expect you to know this part, because this is actually, you know that there's some similarity, but you do not know what is the similarity. It looks like the same, but not the same. In fact, it is the same thing. Okay. To understand the concept of how these three Anova regression works correctly, if you, I don't think anyone want to do stats in uni, right? You do a stats degree in uni, up to here, this point is 1 semester of work already, just on regression alone. Regression is 2 semester work. Okay.
So that means only learning statistics.
You have to use statistics everywhere. There you go. Huh? Okay. All right. So up to here, you are kind of generally safe. My cute little video. Where's my video? Video. Let's go back. Video. Okay. Just go to my statistics and go and look at number 74. I'll show you in Excel. Regression is not necessary. Okay. Yeah. Oh, that one is easy.
Everything is easy.
That one is easy. Okay. All right. Okay. Our studio as far as here, we can close down. Don't need to save. That is fine as well. You love to save so much. Okay, so even this you can close. But what we want is to show you the next part. No, not obesity. Okay. How do you do two-way Anova in Excel? Yeah lah, you produce a data point yourself.
Yeah.
No, don't bother.
Because I love that.
Okay, so in your data analysis toolkit, you realize that Anova, two-way Anova, there's with and without replication. The difference is without replication, that means your experiment has no replicate. One data point for one condition. With replication means that there are multiple replicates, at least 2 or more.
Like the same value.
Okay, that means, let me show you one at a time. It makes it our life easier. Let's say I want to look at your for example, your cell growth. Okay, I have your low salt, medium salt, and let's say high salt. Okay, whatever it means. Okay. Then on the other axis, I can have your low temperature, incubation temperature, medium incubation temperature, and your high incubation temperature. Okay. But because I'm setting up this column as it is, is there replicate or not? No replicate. Because there's only one, let's say only one flask that I incubate in low temperature that's low salt. That means no replicate. Okay. So let's produce some numbers. Do the actual numbers. Maybe this is 60. Okay. Let's say this is 65. Here is 70. Okay. And medium, let's say is 62. 67, 72. And high, 64. 69 and 74. Okay, so it's just addition of 2 each. Okay, so I do a two-way Anova. Is this Should I use with or without replication here? Without. So I do without replication. And just ask me for input range, just like Anova. Select the whole thing. And you have data labels. Okay. So the output range. What? The table. Okay. Very clear. Okay. All right. Okay, in this way, because we kind of generate it this way, right? You cannot calculate because there are no error differences. Because the error here is 0. The mean square is 0. That's why you cannot calculate. Okay. If you play around with the variables, let's say this instead of 60, because we add 2 each. So then the what you call the variance is 0. It's the same. So let's change this to, let's say, 66 and 68 here to 870, and we vary this to 73 and 75. So let's change this, and then repeat the same thing. Okay. Now this is your two-way Anova. So basically, I'm changing the values just to produce some variation in the data set. Actually, anyone can see why is Anova similar to regression?
No, you need more.
Yeah, but think about it here. What do you think is different? To some extent, it does help you appreciate this guy better.
Oh, they say both result and was output error.
To some extent.
Just go to the video.
Indirectly, right? A simple concept is this. If you take regression, if let's say this low sort, medium sort, high sort is a number, and it's a fixed number, right? This average can be the y variable, right? So now you have x and y. Make sense? What you are testing is the gradient equals to 0.
Oh.
Right. Because if the gradient equals to 0, means that these three numbers is not significantly different.
Oh, okay.
Okay. Now, if you have replication, how do you do replication? Correct. Add a few more cells. But Excel have this problem. The sample size must be the same for everything, for every sample. So let's say we add here is, let's say 59, or 59, 63, 63, for example. Here is 65, 69, 71. 69 here, 74, 76. So which means that for the low salt, low temperature, now I have 2 flasks. That's replication. So in order to do that, I use two-way Anova, two-factor Anova with replication. Okay, and I highlight the whole series of data. Yeah, sample rows per mean. That means how many rows I take. So in this case, each sample uses 2 rows. Okay. So each sample uses 2 rows. So that's why it goes 2 rows, 2 rows, 2 rows. And that is the reason why the sample size must be the same. So if the sample size is different, you cannot use this. In fact, it cannot be used at all. 2. Then the output range, just put somewhere. Yeah, correct. What line is blue color? We're talking. Okay. So this is your two-way ANOVA. Your two-way ANOVA with replication, it calculates interaction. Interaction means temperature multiplied by salt concentration. So the temperature and salt concentration affects the growth as well. So fundamentally, that's two-way ANOVA. So you've done that as well. Yay!
So, later we just ignore the depend on the question, then we see whether we
Yep. Okay. Okay, so that's all in terms of this part. And let me stop the recording before we go to the test.